Okay, let's put things on inclines and see what happens. Now, this is a little bit weird, so bear with me here. Okay, so when I put an object on an inclined plane, here's what I'm going to find. And I'll explain this in just a minute. But the normal force with which this pushes against the object is going to equal mg cosine of this angle. And the force with which it's pulled down the ramp is going to equal to mg times sine theta. So gravitation is going to be equal to mg times the sine of this angle, and the normal force is going to be mg times the cosine of this angle. Why? Well, it's kind of weird, but I just had to exaggerate a little bit. So here's a 60-degree incline. Here's the object on that 60-degree incline. Well, gravity is pulling down this way. So if I want to see what the normal force is like, normal force would be this way. So if this is 60 degrees, then this is 60 degrees. So this here is going to be equal to this here, and this here is you see is the adjacent. So this is the cosine of, so 60 times cosine would give me this, and the part that's running parallel to this is this one here, which is opposite from the angle. So that's sine theta. All right. Another way of thinking about it, if you get confused, here's what I recommend you do. This is just a little quick thought experiment. If the angle could be between 90 and 0, let's just say I have it like on a hinge. I lay an object that's free to slide on a ramp that has angle 0. Okay. Well, guess what? It's not going to slide this way. Why? Because the force parallel to this is equal to 0. And therefore, the normal force pushing over is just equal to mg. So what I remember is like, well, what is the sine of 0? Well, the sine of 0 is 0, so there's 0 force going this way. And this would just be equal to the normal force, so that would be cosine of 0 is 1, so that would give me mg up this way. That's how I remember it. Or conversely, you could say, all right, well, let's put it at a 90-degree angle. Sine of 90 is 1, so mg sine theta means it's got the downward force of mg, and now there's no force going this way, so that would just be mg cosine 90. Cosine 90 is 0, so there's no normal force. That's just something I do to help myself remember. Most I do this one here. All right. Now, but the main thing is you should just memorize it. There's another one of those things you just need to memorize because they are going to present you with things rolling down ramps. That is a very common problem setup in AP Physics 1 is to have, I mean, you can almost call the course things sliding down ramps. Okay, so just memorize that the normal force is mg cosine theta, and the down ramp force, the force with which gravity pulls it down the ramp, is mg sine theta. Now, that said, we need to keep in mind that when we draw free body diagrams, we can't draw component forces. So gravity is going this way with mg, and the normal force is a real force, so mg cosine theta is real. But this one here is just a component of this one here, so I can't put that. This one is a real force exerted by this ramp this way, but there's no actual object putting a force on it this way. So I had to be careful in drawing free body diagrams not to draw this as a force. Okay, so let's just try this now. Let's just say I want to write an expression in terms of mg and d. In fact, m is going to cancel right out of this for the velocity of the car upon reaching the bottom of the incline. So what I'd have to do is I'd say, okay, so F equals ma, and in this case, m is the force down the ramp is mg sine theta. So I could say mg sine theta is equal to the mass of this times its acceleration. And if I solve that for acceleration, what I'm going to see is the acceleration down this ramp, which I need to solve this problem, is simply just g sine theta. So because this mass is what's causing gravitation, and this mass is also what has to accelerate, the two cancel out. I just get a equals g sine theta. Which makes sense. It was fine. It was just be g. Okay, so now what kinematic equation do I need to use? Well, I have a displacement. I'm looking for a final velocity, and I know nothing about time. This is my go-to equation. Okay, so now I'm just going to start substituting in. I know that the initial velocity is 0. It's released from rest. And I know that I'm going to substitute a with g sine theta, and I'm going to use d to represent x. And now I just solve this for v, and I just get this, square root 2g sine theta d. Now I have an Atwood machine that has an incline to it. Actually, a pretty common convention here. So what I've got here is I know this is going to come this way. This is heavier than this one. So even if they're just hanging side by side, this one would win. And this is going to be even less than that because times the sine of theta. So I say this is the positive direction. So I'm going to do the sum of the forces equals ma. So what I say is I think I might have something that's here is going to appear in a second if I hit the thing. But anyway, mg sine sum of the forces equals ma. So what are my forces? I have mg 2mg actually pulling this way, and pulling in the opposite direction. I have mg sine theta. Now, these two forces, when added together, are going to equal the mass of the system times its acceleration. So the mass of the system is 3m times the acceleration of the system. Now I just have to solve this for a. So I'm just going to divide both sides by 3m. So here you go. And then I'm just going to simplify it. That gives me 2/3. The m's all cancel out. And that leaves me with 1 minus sine theta. So I end up getting a is equal to 2/3 of gravity times 1 minus sine of theta. So it's a little bit less than this. I knew that was going to happen. I thought there's a blank there. I must have had like one of those things where you hit the button and it appears. Silly me. Okay, let's try one more here. What is the acceleration of the mass shown? How fast is this going to accelerate? And then we'll be done, I think. I hope. Here we go. All right, so now I'm actually using numbers instead of just variables. So I got a 30-degree incline. Mu, in this case, for the kinetic friction between these two, I'm going to assume this thing is moving, is 0.4. And I want to know how fast it's going to accelerate down this ramp. All right. So the first thing I got to do is I got to figure out what the different forces are. There's a component force pulling it this way, and there's a frictional force going the other way. So I got to resolve what those are. So I've got to draw free body diagrams. Well, I don't have to draw a free body diagram, but at least I got to figure out what the forces are. So the force in this direction is going to be equal to mg, which is 60, times the sine of the angle, which is 30. The normal force is going to be mg, which is 60, times the cosine of this angle. That's the normal force. The friction force is always equal to mu times the normal force. So mu times the normal force gives me the frictional force. Now I'm ready to approach it because this one is not going to cause any motion, but these two are. So this one is going to be the positive direction because it's going to slide down. So I'm going to make that my positive one. I'm going to take away this one, and that equals this mass times acceleration. So this gives me 30 minus 2.8 equals 6a. That gives me 9.2 equals 6a. So it's going to accelerate down the ramp at 1.53 meters per second squared. All right, that's it for forces, people. Man, we got 1, 2, 3 units down already. We're doing great. So thank you for watching.